I'll never forget the day when I got a phone call from my advisor, Professor Joseph, and he said, you may have seen on the news, there was an earthquake in Mexico City, and we've been asked to come down and bring the robots. Are you gonna come? What robot are we talking about? So, snake robots. This is what our lab is most known for. When we talk about robots, often an aphorism is that we use them for dull or dirty or dangerous or repetitive tasks. And snake robots are great for all of these. They've got a very tight profile, it's about 2 inches diameter, so it can fit through some very tight spaces into things like pipe networks or small holes in the side of a building. It can also climb up things. So in this case, we're climbing up a tree. It can also climb up pipes. It can fit through sewers. It can also just move across wide, open, sandy areas like a rattlesnake. And it can also climb up people's legs and give them a good scare. So you see it's got a camera on the front. So why would we want this in Mexico City? The Red Cross had invited us down there because they'd seen our robot on the news. And they thought that, so this is an all hands on deck situation, let's get every type of person and every type of thing we can get over here. So we hopped on the next flight down there, and we met up with the Red Cross people, and we rode around in an ambulance with these robots, and we dropped them into collapsed buildings to try to look for survivors or remains. And so here's a video of what it looks like at the disaster zone here. It's on top of a collapsed apartment building. And myself and Dr. Travers, the co-director of the lab, he's right there, he's operating the snake robot with this control case and a joystick. And then I'm over a few feet away with a robot, I'm sticking in a hole to help with a rescue worker. We saw a lot of other tools there that people were using, mostly things like search and rescue dogs, which are great for sniffing out a survivor, and search cams, just a long camera on a stick. But they can really only go so far into a structure before you hit the end of the stick, or the dog can no longer fit into the space. And so this robot can fit into spaces that other people and other tools can't get to, and so we can use it to look for people. And here's a picture of it being sticking the robot in a hole here. So you need one person operates and the other person manages the tether and sticks in the hole. We didn't manage to find anybody with the robot, but we did in this area that they sent us into. I went down about maybe 30 feet into a hole in the side of this collapsed apartment building, and we were able to establish that an open void they were trying to search was actually just an empty water cistern. So there's no people in there. It was perfectly okay for them to go ahead and demolish it and focus their attention elsewhere. And so it really shows that these robots, which is kind of the first time they've been used in like a real life search and rescue situation, can actually come out of the lab and provide value to the search and rescue workers. So great, this robot works out in the field, but there's a problem with it. And that is, it kind of looks like a snake, but it's not very snake-like in the way that we think about controlling it. Now, when an animal thinks about moving, they're not thinking about positions, but rather forces. And a conventional industrial robot, like the kind that you think about putting together cars in an assembly line, they're moving very rigidly and very precisely from position to position. And you don't want to deviate from that position. But when you're an animal, like a person walking, you try to take a step, you're not thinking about, I'm going to put my foot exactly 1 foot in front of me. You're really thinking, I'm just going to put it in front of me and I'm going to support the weight in front of me. And so that sort of force, rather than position, is really the key aspect that lets animals move around the world. And so to do that, we want to move towards newer ways of robots that control forces. So this might be one reason that you see old robots, like an old it's called Honda Asimo, little walking robot, and they kind of stomp around. It's because they're controlling positions and not forces. So our next snake robot now, we start to think about controlling forces and pushing off the world. And so here's the snake robot that we do. We're just telling it to go forwards, and it just blindly pushes off these pegs in the lab. And it starts to look a lot more serpentine. It creeps through these pegboards. It's just sort of pushing off blindly going forwards. We then go ahead and we put this outside, do the same thing but in 3 dimensions, and we start to get this nice conforming property where instead of thinking about exactly where each rock is, it's blind, it doesn't know where each rock is. It's just conforming to the contours of the environment and slithering along. So that's very cool. We can now get cameras into tight spaces, but what about when we want to start moving to doing other jobs? You know, it doesn't have any way of if it detected a leak in a pipe, for instance, you're inspecting a pipe number, it has no way of closing the pipe valve. It has no way of holding objects or delivering packages. It can't move rubble in a disaster. So I know what you're thinking. It needs legs. So we went ahead and build a robot out of these same parts and using the same control principles. Where now it's walking over rough terrain. Again, blindly. There's no cameras or eyes or not a lot of computation. And you see that it's kind of blindly walking over this rough terrain. These rocks proportional to the size. The robot's about this tall, so the rocks proportional to the robot, the rocks are about this big for me. That's pretty cool. It's able to kind of just walk over this. And again, only just by thinking about supporting its weight at each step and not by trying to rigidly place the foot in exactly the right spot every time. It's easy to go from being a snake to being legs because we put in all this work over decades to make the hardware and the software modular. And that means we can interchange the parts. Originally it was devised so that we can make the snake an arbitrary length. But really what this means is that we're now able to take it apart and rebuild new robots on the fly very fast with sort of a Lego set of robot parts. And you can see these black circles on here. On the front and the back are open ports where we can attach extra things like legs or arms or claws or cameras or whatever other kind of thing you can devise that you might need to build a new robot on the fly. And so when I saw this robot, I thought, oh, okay, well, we can put a claw on the front of it. I can, as a challenge to myself, just try to see how we can open a door. And you can see the scale of the robot relative to the doors is pretty hard. The handle would be all the way up here if I was the robot size. And so I'm kind of piloting it with my joystick here. There's still not really any cameras. And we get the door open, and then we deliver this holiday bonus. And of course, if you've been in academia at all, you know that there's no holiday bonus, so that envelope's empty. So that leads us to even more questions that we can tackle here. Like, if you're able to swap the modules on the fly and change the design for any given task, like opening a door or picking up a box, how do we make the behavior automatic too, so that the person has to do less work driving a joystick, so that you don't have to program it a lot? And we want to be able to then transition between these different kinds of behaviors. You want to walk and you want to grab things. And what would be really great is if we can use the same limbs of the robot to both walk and grab things. And so I worked on this project here where we made the robot walk and then changed to using some of its legs, both as legs in this first game. We've got some claws on there, and then it switches over and uses them as arms. And so now we can walk over and grab things, and this would be what you might need to actually turn that valve and close off a loop. And make the multi-purpose. That's kind of like what some animals do. You can use your arms to grab and hold things, or you can use them to climb or walk. And so I know that it's a very, very cool video. I love this video, but I know what you're thinking. It needs more legs. So I went ahead and put more legs on it. It's also got a camera on here. And the idea here is we can now arbitrarily add different numbers of legs and arms and links and cameras and claws and have it scuttle off and crawl away and do the job for us. And we can do this. I don't know why you would want to do this, but it's a job that we can do with the same framework that I did. Okay, now we've got the point where we can make these robots do cool jobs. If you're a robotics PhD student and you know which modules you need to do, you know how to build arms and legs, and you know how to press buttons and all this knowledge that we really want to happen automatically. What we'd really like is for a person to be able, who's not an expert, to take this bag of modules, this bag of Lego set-like components, and build up any sort of robot for any task that they have in mind. And another thing that we look at these robots and have them walking around, but it would also be great if they could be fixed to a table and interact with people. So one thing that is now kind of a hot topic in robotics is called collaborative robots. It's those that can work in close proximity to a person. Instead of those industrial arms that build cars in a cage, you can't get near those, they'll smash your head into pieces. Robots that are smaller scale and more friendly and can work with people. And that can also work in very close proximity to people. And so I'm thinking about these robots and I'm looking in the mirror and I think to myself, needs more legs. And so I went ahead and put the robot on my back and built an arm that's here. It's customized so that what I put in is I wanted to assemble something overhead. This might be a job you would do if you're putting together a car in a factory or if you're putting together an airplane, where currently the worker would have to kind of hold something in place with one hand and use a drill with the other hand and kind of hope that it doesn't fall on their head. Or they have to call over their buddy and have them hold it for you. And so here again, we're using this force control where it's pushing up on the ceiling and not just in the position. So the great thing about this robot too is not just that it's able to do this job, is that every time I show this video to people, and you might be thinking this to yourself, that it could do so much more. There's so many different applications you might have in mind. Everyone has their own vision of the future when they look at this. They say, oh, we can do all sorts of stuff with it. And the great thing is, because of this sort of interchangeability of parts and automatic design and programming of these robots, that not quite at the push of a button, but we're getting there, that you can build this. And so again, I know what you're thinking, you know what I'm thinking, needs more legs. I put another arm on the other side here. And this is, again, just another application you might use where if you're, for instance, assembling something on the side of a building, you're putting on wood panels, what you might have to do is hold on with one hand. If you're standing on a ladder, you hold on with one hand and use the other hand to do the job. And I think that's a waste of an arm. So having an extra helping hand that holds on to you, and it applies the right forces to help stabilize you, so you don't have to do so much effort in keeping your balance. And here I'm doing like kind of a little robot trust ball. It's not quite strong enough to hold my full weight, so I can't lean really back, but it does hold some of my weight. It's a trust ball. I do trust my robots. And so now I'm like halfway ready to take on Spider-Man. Not here, okay. So we put in a lot, the lab as a whole for decades has put in a lot of work to put into getting these robots, and we're really proud of them. We can get really cool videos. But the dirty secret is that we mostly show you success videos. There's a lot of failure videos. For every success, there's many, many failure videos, which people just don't show. And you might look at these videos of success that we show and think, oh, robotics is solved. Let's all go home. Let's use these robots. But really, there's still plenty of work to do. And so here is a robot that's another 6-legged creature, like the previous one, but where it's built out of these bigger modules. And so it's about this tall. And so that enables it to kind of theoretically easily get over human-sized stairs. And so I was demonstrating this robot outside the lab one day to some people, and I said to the guy next to me, let's see if we can get it to walk down the stairs. You know, it can walk over rocks that are pretty high relative to its body height, so this should be easy, right? And so I just went ahead and drove it. And it starts out, right, it's like, looks like it's gonna take a step down the stairs, and it doesn't do so good. I just love how those legs flail like that. It's pretty great. So it kind of shows some of the challenges that we have faced for us in here. Is like, how do we get the robots to respond and adapt automatically to these different kinds of environments? What kind of vision do we need to put on here so that it can see the stairs and know to walk over and know to change over to stair walking? A lot of the videos you'll see of people who do their robots, they have somebody behind the scenes with a joystick and they press a button when they want it to change to stairs or when they want it to change to a different kind of mode. We want to figure out how to do that automatically and not have it do that. Yeah. So I really love working on these robots. There's really nowhere else in the world you can do all these different kinds of robots and build a new one every day and program a new one every day. And better yet, to apply them in the real world, to extend human capability. And to really show that like technology can start to leave the lab, and it's not just in the form of apps. They can make physical changes in the world. They can help people, and that's really what I love about this.